Okay, so let me try and answer that first question. Why should I be bothered to study this distributed systems stuff anyway? What's the point of distributed systems? Well, distributed systems is something that has been around since the 60s. The first distributed system was the bankomat ATM. So the way that you put your card into an ATM machine to get money, that was the first distributed system. Since those humble beginnings, through the emergence of things like ARPANET, which was the US Department of Defense attempt to build a network that could resist a nuclear holocaust, through the rise of the internet and the World Wide Web, through the rise of these e-commerce giants such as Amazon and PayPal, through the emergence of peer-to-peer computing and Web 2.0, what we've seen is continually an increase in the number of services offered on the web, the amount of data being transferred over the web, the number of users of those services, and the number of devices and the number and range and diversity of devices that are being used to access that internet. Even from the point of Amazon, okay, in the early days of the web, in the early 90s, getting on the web involved installing a simple server and writing a few HTML pages. That was you were on the web, and people would have things like my resume, my personal interest page, all that sort of rubbish that we still do to an extent. But as we moved away from bespoke websites towards e-commerce websites, towards social media websites, what happened was we created these portals, these places, these locations on the internet that people would go to. Now, the first problem that was faced by people who became these websites that became popular is that there's a limit on the number of people that can access, the number of connections you can make currently to a machine. Okay, so there are practical limits on the number of users that a single machine can host. So the early problems that people were faced with is, how do I serve my stuff to more users? And that was a revolution in sort of network engineering in terms of the idea of things like load balancers. So I can have two copies of my website and I can dynamically load balance between them, so I can host, if one copy can host 10,000 concurrent users, two copies can host 20,000, three can host 30,000. But even that, the load balancer had limits. So then the load balancer could maybe handle 50,000 users, so you can have 5 sites behind it. But when you got over 50,000, you had to have 2 load balancers with another load balancer, so you had requests coming in and possibly even hierarchies of load balancers, just as the number of users increased. So we had one set of problems of how do I serve my basic content to multiple people, but then the complexity of applications at the back end became more complex. We moved away from just web pages towards web applications. And once we moved towards web applications, we then had the problem of how do we serve content? How does Netflix make sure that you all get that you all get the start of the streaming of your particular program you want to watch within seconds? Okay. Netflix have a bunch of servers that contain all the films you want to watch. They have to somehow deliver those servers to you with a minimum amount of latency. So building that then moved from being able to load balance to being able to cache, being able to keep copies of files. So you have your raw, your basic storage of your files, of your films. Then you have caches that contain copies of films. And caches might be geographically located because in Ireland people tend to watch one particular set of movies. In Germany they're watching other things that they have preferences for. And you have regional preferences, user group preferences, and so on. But why we need to study distributed systems basically comes down to the fact that increasingly any web application you build is going to be accessible by millions and millions of users. If you want to be a success, you have to design that your web application can handle or can scale to handle millions of users from a very early stage. And to just get across that idea of users and user bases, you can see here this red line here represents the increase in number of users of the web over time. So Now you're talking about millions of users. So 500 million users. That was 2002. We're now at probably over 3.5 billion users now. So 7 times the number of users. Okay. So we see the emergence of increased numbers of users. We have a lot more and more hosts. And what we see is simply that, we have to design systems that can scale. Look at Facebook. Facebook has probably over 1.5 billion users using Facebook. How do you build a system that can handle that many users? How many of those 1.5 billion are concurrent? That means how many of those 1.5 billion are accessing Facebook at the same time? Your system has to handle that, and it has to handle it seamlessly. You can't have a page where it says, sorry, Facebook isn't available at the moment. You've got to always be available. You've got to always be able to give the data that users want, as they want, when they want it. So modern software development is frequently based on, can I take processes and can I make them available on the web? People less and less want to have offline systems. They want their systems to be available on the web. They want their back office, so they want to be able to make all of their internal work processes available on web platforms so that they can be more effective. They can work from anywhere in the world. They can scale, okay? And because everyone wants to have all of their stuff on the web, okay? Because you always want to be able to hit the biggest audience you can, you have to design your applications so that they can grow on demand. And the only way to design applications that can grow on demand is to understand how to build distributed applications. I suppose that's what this course is about. So, what are the benefits? Well, the benefits of distributed systems are simply that you can scale your applications and maintain a better price performance. The benefit is that distributed systems allow you to scale your systems. The reason why you'd use distributed systems and not something like parallel computing is that one of the problems that has been seen is that resources such as processors and storage, that they can be increased. You can take a machine and build a bigger machine with more processors, more storage, but there are practical limits over how many processors you can have, over how much you can store on a machine. And once you start getting towards those limits, you have two options. You can move towards complex cluster computing models, but they allow you to continue to scale. But you move into the area of bespoke hardware, okay? And building clusters is expensive. Building higher level machines is expensive. The better solution is to say, let's stop trying to keep building bigger and better machines. Let's make our system, let's distribute our system. Let's move it over multiple machines. Let's move away from the single machine, the monolithic machine mentality, towards multiple machines, towards distribution of our program over machines. Because if we distribute and we use commodity hardware, then the cost of distributing becomes that. If we buy a commodity server for 20 grand, okay, you might be able to by having 3 20 grand servers, you might be able to get the same performance as spending building one 100,000 euro server. That's custom. Okay. The other benefits, though, are there's a price performance benefit that comes by using commodity hardware. That was one of the things that Google did when they started up. One of their selling points was that they built their own systems. They built their own version of Linux. They built everything from the operating system up so they could use commodity hardware. Because if they could use commodity hardware, they had wide availability of hardware that they could purchase at low costs, and they could then simply deploy their system onto more servers, and they could scale better. They could scale. The cost of scaling came down, and that meant that they could maintain the performance levels they wanted, the quality of service requirements they had, without having to spend too much money. So the idea is that they're able to scale up. The idea is that they're able to scale out their systems rather than having to scale up their systems, rather than having to create more and more bespoke and expensive custom servers, which is what scaling up the hardware. They instead move towards, and we should always all instead move towards models where we simply scale out our system. We can essentially create more copies of our system. And so we can essentially handle load by having multiple copies of the system. I suppose one of the things we'll talk about later on when we talk about microservices is that scaling out has moved from making essentially carbon copies of the whole system to trying to make copies of bits of the system. To move from a high level of granularity, where we consider just the system and, okay, this is our system. We scale out by buying another server, we install the entire system on the other server, and then we load balance between it, to saying, looking at which bits of the server, which bits of our system need to be scaled, and scaling only the parts of the system. And that's where microservices comes in as a solution. It allows a much more fine-grained view of how we scale. But the benefits then of distributed systems are, not only do we get this price performance benefit from using commodity hardware and using a distributed approach rather than using scaling up the hardware or going for bespoke stuff like clusters, we get this reliability, sort of fault tolerance benefit. If we scale by having multiple copies of our system over multiple machines, then if one machine fails, the other machines will continue to run. So that means that the service becomes more reliable. Okay, it's able to handle more failures. I remember I had a PhD student who came and worked with me, and he'd worked for Nokia Siemens, and he'd been working on the large distributed database that sat behind all of the Nokia phones. This was in the 2000s, before Nokia died and was resurrected. But it had this massive database that used for handling all the IMEIs and the phone numbers and things like that. And that database was so big that frequently there were any number of nodes within that distributed database that have failed at any point in time. And in fact, it was so big that the team that built the system didn't actually understand, could not actually monitor the system effectively, and they often didn't know where those failures were until a bigger failure happened, at which point, we see a big failure over there, now we can tackle it. So distributed systems give you price performance benefit. By using commodity hardware, you're able to keep the price down, but still maintain levels of performance. They also give you reliability. So by distributing, you have copies, replicated data, redundancy of functionality. So if a service fails or if a database fails, often, in most cases, your system will still operate and you're still able to provide a level of service. And then the reason why we might consider distribution is because some applications just are distributed. There's no way around it. They're just naturally distributed applications. They can be distributed because users are geographically located, so they can be distributed because they're on the web. There are many reasons. However, the downside, or the issue when we talk about distributed systems, I'll jump forward, is that whenever we move from a standalone system towards a distributed system, we introduce this new component, this thing called the network. And networks are not these beautiful things that work seamlessly. They're things that have performance limitations. They require the design of protocols to manage the interaction between the components. And as a result, they introduce potential new points of failure. So not only can the application fail, the network can fail. And when we design distributed systems, we have to try and design them in a way that they can survive not only the failure of a node, but also the failure of parts of the network. And this is this CAP theorem, or the Brewer's theorem, which I'll talk about a little bit later. The other issues related to the introduction of a network components is that because we have a distributed system, the system is spread over multiple nodes. We don't just have to secure the one machine that contains the program. We have to now secure all of the machines that are part of the program, and we have to secure all of the communications between those machines. And finally then, adding a network in there, adding this distribution, increases the complexity of the software. It makes it more difficult for us to build the system. The individual bits often become easier, but how you link them together can become much more complex. And trying to understand and debug a program that is distributed is degrees of complexity, is significant degrees more difficult than debugging a standalone system. Finally, when we move from a standalone system towards a distributed system, people make assumptions. They assume, for example, that the network is reliable. That's not the case. The web has a complex infrastructure. The internet is a complex system. At any point in time, different parts of that system are failing. Okay? It's not reliable. A connection, a wire from A to B, is not guaranteed to work. It's not secure. People can spoof, they can eavesdrop, they can do tamper, they can do all of the things that you'll have talked about on any information security course. It's also a heterogeneous place. There are different types of cables, there are different types of nodes, there are different routers, there are different gateways. It's not a homogeneous environment, it's a heterogeneous environment, and not everything is implemented exactly the same. So you can get small trade-offs between, or small issues can arise between components that are not 100% compatible. The topology, as I say, the internet is a complex system where there's always something failing. So the topology of the internet is changing all the time. New machines are being added, new services are failing, and so on. It's a constantly evolving network. And the latency, the time it takes to allow one node to connect to another node is not so another problem is that the time it takes for one node to connect to another node is not zero. We often assume that just because two machines are quite close together, we can get instantaneous. So when we run an application on our desktop, and it's, in Docker, everything works fine. When we move it to a network, and we distribute it actually over a network, we can find that problems arise because we've made assumptions about the interactions between things. We've assumed that the latency is zero and that the response is immediate. Sometimes the latency can be big, and it can mean that services can wait and we can get timeout issues and all sorts of problems. We also often assume we have infinite bandwidth. Those cables can only take so much data at a time. If you're trying to push millions of users through your system, you're going to have bandwidth issues. And then we have assumptions like the cost is zero. So that's probably the most true assumption that we have there, that typically the cost is zero. But I suppose where this matters is that in the past we've had situations where you have users that are on pay per byte connections. It doesn't happen very often now, but in the old days, when I was young, you'd have lots of users who were there and they would have to pay for the data, pay for their connection. They have to pay per byte of data. So if you build a system that's very data intensive and it's maybe sending out really high resolution images, for example, then you can be billing somebody a lot of money. And somebody may not use your system because the cost of using the system to them is not worth the benefit of using the system. Okay? And finally, people often assume there's one administrator. There's not. There's no single oversight of the web. In fact, nobody knows how big the web really is. We have all these assumptions and all these estimates, but the web is just too big. The web goes all over the world. Okay? And that's just the web we know about. There's the millions of devices, and it's only going to increase. And each set of devices has different administrators with different preferences, different philosophies, and handling all that can be difficult. So, I hope that I've explained why you need to study distributed systems. In a nutshell, you need to study distributed systems because everything we do now is distributed. We all use the web, we all interact with services over the web. Everyone wants to provide their services on the web. Everybody wants their stuff in the cloud. Increasingly, we have to consider that we have to build systems that can scale to handle increased numbers of users. If we build our web application, we build our new latest music sharing application or latest online media box. Okay, we have to build that system in a way that can scale. And the only way you can build systems that scale is to design them as distributed systems. The only cost-effective way. You can design them as clusters, you can design them to work on really high-power machines, but ultimately, hardware has its limitations. and you either move to cluster computing, which is also expensive, or you move to commodity off-the-shelf computing, which is cheaper but more complex to do. Okay. Hopefully that's persuaded you. So what I'd like to do now is I'd like to stop this lecture. I'm going to then start the next lecture, which I'm going to work through a simple example. We're going to go look at that first example of distributed system, the bankomat ATM, and just consider a little bit about what are the implications of building that bankomat ATM system as a distributed system.